Let's have a look at resisted motion. So we take into account resistance. So remember, resistance is always in the opposite direction to motion. Okay? That was Newton's third law. Basically, we can bring it down to three cases. So the first case is if we're simply going in a horizontal line. So we're going that way. But if we're talking about horizontal motion, well, gravity plays no part in that. We know there's no force due to gravity. I'll define the direction I'm going in as the resultant force. And unless they tell me otherwise, there are no other forces. But because I'm moving in a certain direction, there must be a resistance going in the opposite direction. So that is the force. And so, like I did with the last lot of questions, the way we set the question up is we say, well, our resultant force must equal all the other forces added together. In this case, there is only one. It's R, and it's in the opposite direction. So we'd get minus R. I'd then divide through by mass, come up with an acceleration equation, and do whatever we have to do then to solve the problem. So that would be horizontal. Now, if it's vertical, we've got two cases of vertical motion, because we could be travelling up. And so in this case, I'll define up to be positive. I'll have the force due to gravity, which goes down. And now we'll also have resistance as well. There'll be some sort of resistance. So when I set this equation up, I'll say, well, the resultant force is equal to all of the others, but all of the others are all in the opposite direction, so both of them are negative. I'll have minus mg minus r, divide through by the mass, and again, we'll come up with an equation, whatever we have to do with that. So, notice, just because we've added resistance doesn't change what happens. I mean, the greatest height is still going to happen when velocity equals zero. It's still, before I come back down, I'm still going to stop. That doesn't change. Downwards motion. Now this time I'm going to define down to be positive. I always like to make the direction in which I'm travelling to be positive. So gravity, that is going down, but it's now going to be a positive force because it's now in the same direction as which I'm travelling. But resistance is always in the opposite direction. So this time we'd get an equation like mg minus r, divide through by mass, and there we go. Now, there's a new term we need to talk about, which is called terminal velocity. Now, terminal velocity happens, as you can see there, when acceleration is equal to zero. So in other words, it's like saying the forces are all balanced. So we're travelling down, but we would get to a point where we'd be travelling with a constant velocity because the acceleration is zero. Okay, let's do a typical sort of problem. We're going to project upwards velocity of u for initial velocity in a resisting medium. Assuming that the retardation due to this resistance is equal to kv squared, find expressions for the greatest height reached and the time taken to reach that height. Okay, let's draw a little picture so we can see what's happening. We're going up. My resultant force is up. Now let's put all the other forces on there. I have a force due to gravity, mg. But I now have this resistive force, which they've told me is equal to kv squared. See, retardation is a force. Okay? So I don't multiply that by mass. Now what do I know? I know that when displacement is zero, velocity was u. So let's set it up. Acceleration is minus mg minus kv squared. So acceleration will be minus g minus k on mv squared. I have acceleration in terms of velocity. I want to find an expression for the greatest height. So that's displacement. And also the time to reach that height. So that's time. So the first thing I'm interested in is displacement. So somehow I would like to link that velocity and displacement. So the term for acceleration that links velocity and displacement together would be the v to v dx, okay? Because it's in terms of velocity. So I couldn't use the d dx of a half v squared, which also links displacement and velocity, because there I would have to integrate with respect to displacement, but my formula's in terms of velocity. So I use v to v dx. Now it's with respect to v, so I want to turn upside down. And because I've turned it upside down, it's convenient all to be one fraction as well, you'll notice. So I now have mv over minus mg minus kv squared. Okay, so x will equal, my displacement is going to be, I'm going from a velocity of u, was the initial velocity, up to a velocity of 0, because we're finding the greatest height, and the greatest height occurs when velocity is 0. Okay. V on mg plus kv squared, going to be a log, because m and g and k, they're all constants. Basically, we've got v on v squared, derivative on function. So I know I've got to turn this into a log function. I want the derivative on top, so I'd like 2kv on top. That'll give me the derivative of the bottom of the fraction. To balance it out then, I'll put 2k at the front. You'll notice the other thing I've done here is I've got rid of the negative by swapping the limits around. So we get m on 2k out the front. It's the log of mg plus kv squared. Now, sometimes I leave this step out because I know log laws, I can always bring it in and go straight to a fraction. So sometimes I'll just go log of, substitute in for u, that'll go on the top of the fraction, substitute in for 0, that'll go on the bottom of the fraction. This time I've done the step in the middle, but remember log laws, log minus log becomes log divided by. Now, so there's mg plus ku squared on mg. I probably could leave it like that, but mg on mg, of course, is 1 and ku squared. So I now have the greatest height. Ugly looking thing, but it is what it is. So there's my greatest height. The other thing it asked us for was the time it takes to get there. So I'm going to go back to the acceleration equation. Now I want something that links velocity and time together. Again, it's in terms of v. So I want d v to t this time for acceleration. So I'll use d v to t, because I can turn this one upside down. It'll still be with respect to v, but now it'll find an expression for time. My integral now, of course, is different. I've now got d v on mg plus kv squared. That's going to be an inverse tan. Right? Remember, it's a squared plus x squared on the bottom of the fraction. So let's make it look like inverse tan. Our standard integral for inverse tan is, as I just said, a squared plus x squared. So I'm going to take the k out. So I've just got v squared, but it now means my mg becomes mg on k. Now, integrate, we get 1 on a. A in this case will be the square root of mg on k. So 1 on a, turn it upside down, square root of k on mg. And then it'll be inverse tan of x on a, well x in this case is v, and again a is the square root, or the reciprocal of a is the square root of k on mg. All right, I've tidied up my constants. The m and the square root of m cancel to give me the square root of m on top. Square root of k and k also cancel, square root of k, and I've still got my square root of g there. Now, inverse tan, sub in u, sub in 0, well, inverse tan of 0 is 0. There is an expression for the time it takes to get up there. Without knowing what the mass is and all the other information, that's the best we can do. So that's how long it will take. So, all right, let's try another one. This time we're going to be going down. Body of mass, they've told us the mass this time, 5 kilograms, dropped from a height at which the gravitational acceleration is g, assuming air resistance is proportional to the speed v, that constant of proportion is an eighth. Find the velocity after time t. All right, let's come up with an acceleration formula. This time I'm going down. So my resultant force is down. Notice I put 5 because they've told me the mass is 5. Gravity will be mass times g, well, so it's 5 times g. My resistance is 1/8 v. They've told me it's proportional to the speed, that constant of proportion being an eighth. Okay. So setting up our equation then, the resultant force must equal the sum of the others. So we get 5g minus an eighth v, divide everything by 5. I've got g minus 1/40th v. We want velocity and time linked together. It's in terms of velocity again. So again, I'm going to use dv to t for acceleration. That'll allow us to link velocity and time together. Make it all one fraction because I'm going to have to turn it upside down. And I've made it a definite integral because we're starting with a velocity of 0 because we're just dropping it, so it has no velocity. And we were coming up with a general formula, so it's coming from 0 to a velocity of v. What do we got? We've got a log situation again, haven't we? Because we've just got a polynomial on the bottom, which is power of 1, and on the top we've got a constant. So on the top of this fraction, I actually would like minus dv. Well, that's all right. I'll just take the minus out the front, so I've got minus 40 instead of 40, and we've just got the log of 40g minus v, sub in 0, and we have 40 log 40g there. But the problem is with this one, this is time in terms of velocity, and the question has asked for velocity in terms of time. All right, we're going to make v the subject of this wonderful thing. I've multiplied both sides by 40. Sorry, divided both sides by 40. So t on 40. Now we'll undo the log. So to undo the log, we exponentialize, if there is such a word. So e to the power of t on 40. Now, v is in the bottom of the fraction. So let's turn it upside down. So v is now on the top of the fraction. But that means it's now e to the negative t on 40, because I've got to turn the other side upside down as well. I can now multiply by 40g. Then I can move the 40g over and multiply everything by -1. I've got an expression for velocity in terms of time. The terminal velocity. We have two ways of doing this. Remember I said terminal velocity is when acceleration equals 0. Our acceleration formula, sure enough, make it equal 0, we get 40g. And we could do it using limits. And the limit as t approaches infinity of a negative exponential, think of your curve, it approaches the axis, so it's going to be approaching 0, so I just have 40g. So either way, that's how you could work out our terminal velocity. How far has it fallen after time t? So now we want a displacement time. But we've just worked out a velocity time. So dx to t is 40g, 1 minus e to the minus t on 40. I just got to integrate, because it's already in terms of t. I don't have to turn this one upside down. We're going from time 0 to some random time t that we want. Integrate an exponential. And don't forget to integrate the 1 as well. So we've got a t there. Sub in t, sub in 0. And we have this lovely looking expression for displacement. So I didn't bother going back to acceleration this time, because we'd already worked out a formula for velocity in terms of time. They wanted a formula for displacement in terms of time. So really it's back to 2-unit idea. If I want to go from velocity to displacement, and we're talking about in terms of time, I just integrate. Okay, so we have our Cambridge exercise 4a and 4b. They're on our resisted motion. In Patel, picked out a few out of 8c you might want to have a go at there.